Hi. In this video, I'm going to talk about one of the most popular algorithmic problems from LeetCode, which is the two-sum problem. If you're new to programming or just starting your journey on LeetCode, this is a great problem to start with. So, what is the two-sum problem all about? Well, the two-sum problem is a classic algorithmic problem that, believe it or not, it can be challenging to solve. But you don't need to worry, because in this video, we're going to tackle it step by step. We'll start by a clear breakdown of the problem statement, understanding what exactly we are trying to accomplish. From there, we'll explore different methodologies and solutions, including the brute force approach, the two-pointer approach, and hash tables. We'll analyze the time and space complexity of each solution to determine which solution is the most efficient. And by the end of this video, you'll have a solid understanding of how to solve the two-sum problem efficiently, no matter how challenging the input array or the target value may be. Now, there are many ways to solve this problem, but in this video, I'm going to explain 3 of them. First, we'll look at the brute force approach, which is not the most efficient, but it's a good starting point to understand the problem. Then we'll move on to the two-pointer approach, which is faster than the brute force approach, but it requires a sorted array. Finally, we'll explore the hash table solution, which is the most efficient of the 3 and can handle unsorted arrays. But before we dive into the solutions, let's take a closer look at the problem statement to make sure we understand it well. Once we're on the same page, we'll get started with the solutions. Alright, that's enough for the introduction. Let's jump right into it. When solving a problem, having a clear understanding of the problem statement is crucial. So let's take a look at the statement for this particular problem. The problem states that, given an array of integers, nums, and an integer target, return indices of the two numbers such that they add up to the target. This means that you are given a list of numbers, which we will call an array, and another single number, which we will call the target. And the list of numbers are made up of integers. This means that they are whole numbers, like 1, 2, 3, and so on. And you need to find 2 numbers in the array that add up to the target value and return their positions in the array. These positions are called indices. So basically, indices is just a fancy way of saying positions, which are just numbers that represent where a particular item is located in a list. Now let's move on to the second paragraph. You may assume that each input would have exactly one solution, and you may not use the same element twice. This means that for a given input of an array of integers and the target value, there is only one solution to the two-sum problem. In other words, there is only one pair of numbers in the array that add up to the target value. And you cannot use the same number in the array twice to add up to the target value, unless the number appears in different positions in the array. For example, if the array is 1, 2, 3, 4, and the target is 6, you can use 2 and 4 to get the target, but you cannot use 3 twice, unless there was another 3 located in the array. Finally, let's look at the last paragraph. You can return the answer in any order. This means that when you find the indices of the 2 numbers in the array that add up to the target value, you can return them in any order you like. For example, if the indices are 2 and 5, you can return them as 2 and 5 or 5 and 2. Either is fine. Let's look at an example to understand the problem statement better. Suppose we have an array of integers 2, 7, 11, and 15, and a target value of 9. We need to find 2 numbers in the array that add up to 9. From the given array, we can see that 2 and 7 add up to 9. So the answer should be the indices of 2 and 7, which are 0 and 1. Let's take a look at another example. Consider the following array of numbers: 3, 6, 2, -9, and 4, and a target value of 6. At first glance, it may seem that the number 6 in the array is the solution to the problem. However, we are not looking for just any number that equals the target value. Instead, we are looking for a pair of numbers in the array that add up to the target value of 6. So in this case, there is only one pair of numbers that add up to 6, which are 2 and 4. The number 6 by itself is not a solution to the problem. This highlights the importance of understanding the problem statement and requirements before attempting to solve it. Before we dive deeper into the solutions, let's also understand the constraints given in the problem statements. If you have ever wondered why some problems in computer science have constraints on the input size, well, let me explain it to you in simpler terms. The reason behind these constraints is to make sure that the problem can be solved in a reasonable amount of time and space. Imagine if the input array could have unlimited number of elements. Solving the problem efficiently could be very difficult or even impossible. So by limiting the maximum size of the input array, the problem becomes more manageable and easier to solve within reasonable time and space constraints. This way we can ensure that the computer can handle the task efficiently without slowing down or crashing. So the problem statement lists the following constraints. The first constraint states that the length of the input array nums is between 2 and 10 to the power of 4. This means that the array must contain at least 2 elements and can have a maximum of 10,000 elements. The second constraint states that the elements in the array, nums of I, can range from -10 to the power of 9 to 10 to the power of 9. This means that the elements can be any integer value between -1 billion and a billion. And the third constraint states that the target value can also range from -1 billion to 1 billion, just like the elements in the array. Finally, the last constraint states that only one valid answer exists. And that means that there will always be a unique pair of elements in the array that add up to the target value. Okay, let's get started with the solutions. The two-sum problem is a relatively simple problem to solve, but the solution for this problem is not as simple as it may seem, because it can be tricky to find an efficient solution that works for all cases. As I mentioned before, there are many ways to solve this problem, each with its own time, complexity, and efficiency. But for the sake of this video, I'm going to explain 3 of them. These 3 main approaches are brute force, 2 pointers, and hashing. The brute force approach is to simply iterate through the array and check each pair of numbers to see if they add up to the target. For example, let's say we have an array of 3, 5, 2, and 11, and a target value of 13. To use the brute force approach, we start by checking the first element with all the other elements to see if they add up to 13. So we check 3 and 5, 3 and 2, and 3 and 11. None of these pairs add up to 13. So we move on to the next element, which is 5. We check 5 and 2 and 5 and 11. None of these pairs add up to 13 either. We continue checking each pair until we find the pair 2 and 11, which adds up to 13. The brute force approach is easy to understand, but it can be very slow for large arrays. In fact, its time complexity is O of n squared, which means that for an array of n elements, it takes n squared comparisons to find the 2 numbers that add up to the target. So for a very large array, this approach can be very slow and inefficient. Now let's see how we can implement this in code. I'm going to be using Python for this. This is how the code would look like. So let's break down the code step by step. First, we define a class called solution with a method called toSum. This method takes in two arguments, nums, which is the list of integers, and target, which is the target sum we're trying to find. Then here we have a for loop that will go through each element in the nums array one by one. The range function gives us a list of numbers from 0 to the length of the nums array, and the for loop goes through each of those numbers and assigns them to the variable I. Inside the first for loop, we have another for loop. This for loop will go through every other element in the nums array, starting from the element after the one we are currently looking at. That's why we have a I plus 1 as the starting point. We assign each of these other elements to the variable j. And then we have an if statement that checks whether the sum of the two numbers we're currently looking at, which are nums I and nums j, is equal to the target value. If it is, we found the two numbers that add up to the target value, and we move on to the next line. And this line returns the indices of the two numbers we found as a tuple. The tuple contains two values, I and j, which represent the indices of the two numbers in the nums array that add up to the target value. And that's it. We use two loops to look at every possible pair of numbers in the list, and we add them together to see if they equal to the target number. If we find two numbers that add up to the target number, we return their positions in the list as a pair. So for the time complexity, since we compare every element in the array to every other element, the number of comparisons we make increases with the square of the length of the input array. This means that the time complexity of this solution is O of n squared, where n is the length of the input array. And as for the space complexity, we only need to store the indices of the two numbers that add up to the target value. So the space complexity is O of 1, which means it uses only a constant amount of memory. Another solution for this problem is to sort the array and then use two pointers, one starting from the beginning and one starting from the end, to traverse the array and find two elements that add up to the target value. This is called the two pointers approach, and is a simple and easy to understand algorithm. The algorithm works by first sorting the array in ascending order. Then we use two pointers, one starting at the beginning of the array and the other one starting at the end. If the sum of the values of the two pointers is less than the target, we move the first pointer forward to increase the sum. This is because the array is sorted in ascending order, so moving the left pointer to the right will increase the sum. If the sum is greater than the target, we move the second pointer backward to decrease the sum. If the sum is equal to the target, we have found our answer and we return the indices of the two elements that add up to the target. The time complexity of the two pointers approach is O of n log n because of the sorting algorithm that is used. Sorting an array of n elements takes O of n log n time complexity. Once the array is sorted, we use two pointers to go through the array once. This step takes a certain amount of time too, which is based on how many numbers there are in the array. We write this time complexity as O of n. So the overall time it takes to solve the problem with the 2 pointers solution is the time it takes to sort the array plus the time it takes to go through it with the 2 pointers. And this is written as O of n log n plus n, but we can simplify it to just O of n log n. This means that as the size of the input array gets bigger, the time it takes to solve the problem increases, but not as quickly as it would with other methods like the brute force approach. The brute force approach takes much longer because it has a time complexity of O of n squared. And for very large arrays, the 2 pointers approach will still be slow. And we also need to create a sorted copy of the input array, which takes up extra memory. So the space complexity for the 2 pointers solution is O of n. Here's the code for the 2 pointers solution. Let's break down the code and walk through it step by step. Again, we first have our class and method definitions. Next, we sort the nums list using the sorted function and store it in a new variable called sorted nums. Then we initialize 2 variables, left and right, to keep track of the indices of the 2 pointers. Left starts at index 0, the beginning of the sorted list, and right starts at the last index, the end of the sorted list. And the reason we set right to len of nums minus 1 is because len of nums gives us the length of the input list nums, which is the total number of elements in the list. Since Python indexing starts at 0, the last element in the list has an index of len of nums minus 1. Therefore, by setting right to len of nums minus 1, we are initializing the pointer to the rightmost element in the list. And then we enter a while loop that continues as long as left is less than right. Inside the loop, we calculate the current sum of the values at left and right indices. If the current sum is equal to the target, we have found the 2 numbers that add up to the target. We store these numbers in variables a and b. Now, what do we have going on in this block of code? This block of code is used to handle the situations where the 2 values a and b are equal to each other, which means that we have multiple occurrences of that number in the nums list. In this case, we cannot simply use the index method to find the index of the second occurrence of the number, because that would give us the same index as the first occurrence. To find the correct indices of both occurrences, we need to use a slightly different approach. First, we use the index method to find the index of the first occurrence of the number a. Then we use the index method again to find the index of the second occurrence of the number b. But this time we start searching from the index of the first occurrence of a plus 1. The index method is a built-in Python method that returns the index of the first occurrence of a given element in a list. In the case of this code block, nums.indexA returns the index of the first occurrence of the variable a in the list of nums. When a is equal to b, we want to find the index of the first occurrence of a, and then we want to find the index of the first occurrence of b after the index of the first occurrence of a. We accomplish this by calling the index method a second time, but this time we include an additional argument, which is a underscore index plus 1, which tells Python to start searching for the index of b after the index of the first occurrence of a. This ensures that we find the index of the first occurrence of b that comes after the index of the first occurrence of a. Now, I understand that might be a bit confusing. So let's take a look at an example to understand this better. Suppose we have the input array nums as 3, 1, 4, and 3, and the target sum as 6. We sort the array to get 1, 3, 3, and 4, and start with the left pointer at index 0, which holds the value 1, and the right pointer at index 3, which holds the value 4. The current sum is 1 plus 4 equals to 5, which is not equal to the target sum. So we need to adjust our pointers to get closer to the target sum. In this case, since the sum is smaller than the target, we can move the left pointer to the right to get a larger number. So we move the left pointer to index 1, which holds the value 3. Now the current sum is 3 plus 4 equals to 7, which is larger than the target sum. Since the current sum is now larger than the target, we need to adjust our pointers again. But this time we move the right pointer to the left to get a smaller number. So we move the right pointer to index 2, which also holds the value 3. Now the current sum is 3 plus 3 equals to 6, which is equal to the target sum. So we have found the pair of numbers that add up to the target sum. Now we need to find the indices of the two numbers 3 and return them in a list. As we can see, the two occurrences of the number 3 are at indices 0 and 3. But since they are equal to each other, we cannot use the index method to find the index of the second occurrence of the number. So we use the block of code we just discussed. We first find the index of the first occurrence of the number 3 using the index method, which gives us index 0. Then we use the index method again to find the index of the second occurrence of the number 3. But this time we start searching from index 1, which is the index of the first occurrence of 3 plus 1, which gives us index 1. Finally, we return the two indices as a list, 0 and 3. And when a is not equal to b, we simply call the index method twice, once for a and once for b, and return a list containing the two index values. And if the current sum is less than the target, we increment left to move the pointer to the right. And if the current sum is greater than the target, we decrement right to move the pointer to the left. Finally, if we've gone through the entire list and haven't found a pair that adds up to the target, we return an empty list. So that was it for the two pointers approach. Now let's move on to the hash table solution. The hash table solution is a highly efficient way to solve the two-sum problem. It provides a significant improvement over the brute force and the two pointers approach. The hash table approach involves using a data structure that maps keys to values, with keys representing the numbers in the array and the values representing their indices. The core idea of this solution is to iterate through the array just once and store the indices of the numbers that have already been processed in the hash table. This allows for a significant reduction in the number of iterations required and eliminates the need to look at every possible pair of numbers. So to understand the hash table approach, imagine you have a special book with a list of phone numbers and names. When you get a call from someone, you can quickly look up their name in the book to see who's calling. The hash table approach is like that book, but instead of phone numbers and names, it stores numbers from the array and their indices. So here's how it works. You start by looking at the first number in the array and figuring out what number you need to add to it to get the target number. This number is called the complement. For example, if the first number is 2 and the target is 9, the complement is 7 because 2 plus 7 equals to 9. Next, you check if the complement is already in the hash table. If it is, that means you've already seen the number you need to add to the current number to get the target number. So you're done. You can return the indices of the two numbers and be happy. If the complement is not in the hash table, you add the current number and its index to the hash table. This way, if you come across the complement later on in the array, you'll be able to find it quickly in the hash table and know immediately that you've found the two numbers you need. The hash table approach is faster than other solutions because it lets you look up numbers quickly instead of checking each possible pair of numbers in the array. The time complexity of the hash table approach is O of n, where n is the number of elements in the array. This is because we only need to iterate through the array once, and each lookup in the hash table takes constant time on average, assuming a good hashing function. The space complexity of the hash table approach is also O of n, because in the worst case, we would need to store all n elements in the hash table. Overall, the hash table solution is a highly efficient approach to the two-sum problem. Now, this is what the code looks like for the hash table solution in Python. Let's break down the code and explain each line. Again, we first have our class and method definitions. Then this line creates an empty dictionary called num indices, which will be used to store the indices of each number in the nums list. Then this line starts a loop that goes through each number in the nums list and its corresponding index using the enumerate function. The enumerate function in Python is a helpful tool that lets you loop through a list and get the index and the value of each item at the same time. It returns a special object that you can use in a for loop to get the index and value of each item. So by using this function, you can easily keep track of the position of each item in the list. This is useful when you need to store the value and index of each item in a dictionary or perform some other operations. So then we have this line that calculates the difference between the target value and the current number and stores it in a variable called complement. And then here we check if the complement exists in the num indices dictionary. If it does, that means we have found a pair of numbers that add up to the target value. So we return a tuple containing the indices of the current number and its complement. And then this line adds the current number and its index to the num indices dictionary. And then if the loop completes without finding a pair of numbers that add up to the target value, an empty list is returned. Let's look at an example to understand it better. Let's say we have an input array of 2, 5, 7, and 11, and the target value of 9. And we want to find the two indices that add up to 9. So first we create an empty dictionary, num indices, to store the indices of each element in the array as we loop through it. Then we loop through the array using the enumerate function to access both the elements and their indices. On the first iteration of the loop, I would be 0 and num would be 2. We calculate the complement of the current element with respect to the target by subtracting it from the target. In this case, the complement would be 9 minus 2 equals to 7. Next, we check if the complement exists in the num indices dictionary using the in operator. Since 7 is not yet in the dictionary, we move on to the next iteration of the loop. On the second iteration of the loop, I would be 1 and num would be 5. We calculate the complement of the current element with respect to the target. In this case, the complement would be 9 minus 5 equals to 4. Next, we check if the complement exists in the num-indices dictionary. Since 4 is not yet in the dictionary, we move on to the next iteration of the loop. On the third iteration of the loop, I would be 2 and num would be 7. We calculate the complement of the current element with respect to the target. In this case, the complement would be 9 minus 7 equals to 2. Next, we check if the complement exists in the num-indices dictionary. Since 2 is already in the dictionary with a value of 0, which is the index of the first element in the array, we return the indices of the current element and its complement as a tuple. So in this case, the function would return 0 and 2. And that's it for this video. I hope you found it useful, and until another video, bye.